Is it possible to put out the sun? For example, what would happen if we poured all of the Earth's oceans on it? Or even more water? Well, let's find out. The universe is a place full of mysteries. Since ancient times, scientists have been arguing about how space works. But none of us has ever doubted the existence of one thing: the sun. The center of our solar system. It's big, bright, and immortal? Nah, not really. Actually, the sun is just an ordinary star. It consists of 75% hydrogen, a little helium, and a pinch of other heavy elements. Gravity holds it all together. But in around 5 billion years, the life cycle of the sun will come to an end. The hydrogen inside it will run out. Our star will begin to grow gradually, and you can't even imagine just how big it will become. And then it will start eating all the nearby planets. That's when we'll regret being so close to it. After eating us all, the star will remain a red giant for another billion years or so. And then, sooner or later, it will begin to shrink and fade, turning into a white dwarf. In the end, nothing will remain of it but a bright and colorful planetary nebula. But don't get scared. Right now, the sun is in the middle of its life cycle. It was born about 4.5 billion years ago, and about the same amount of time remains. Fortunately, we were born during the star's best and most stable period. In other words, there's no reason to worry. So let's find one. How about speeding up the sun's life cycle with the help of water? We'll try to collect all the water on Earth and pour it onto the sun. First, we'll need a bucket. No, not this one. We'll need a really, really big bucket. The one that can contain around 326 million cubic miles of water. It will be equal in size to the distance from Washington to Chicago. Or if we can only find ordinary buckets, there should be around 70 quintillion of them. This is a number with 18 zeros. Okay, imagine that we magically got that many buckets. It's time to put out the sun. We splash the star with all this water and nothing? Seriously? Oh, just look at this. The sun has probably felt sorry for us and produced one little solar flare. It turns out that all water on Earth is actually just a pathetic drop for the sun. People often underestimate how much bigger the sun really is than our planet. In reality, it can fit more than 1,003,000 Earths. So yes, the sun won't go out or even get colder. It won't even notice that we've done something. But let's not give up. We really want the sun to go out for some reason. What happens if we pour just enough water on it? And how much is this enough? Remember our quintillions of buckets? Well, we actually need about 370 octillions of them. This number has 27 zeros. It's hard to even imagine, so let's just say that it's a lot of water. Now, let's splash it all over the sun again. Wow, just look at the steam! But the sun hasn't gone out again. On the contrary, it said thank you and suddenly became much bigger and brighter. What's happening? You see, the sun isn't actually a campfire. Inside bonfires, candle flames, there's a chemical combustion. When we pour water on the fire, the water absorbs the heat of the flame and cools it to such an extent that it can no longer maintain the burning reaction. It also blocks the fire's access to oxygen. Water basically stops the chemical process. But the burning of the sun isn't the same reaction. Even though we say it burns, it's not entirely true. What happens there is called nuclear fusion. It's one of the most violent and craziest reactions in the universe. There are many layers of hydrogen going deep into the sun. If you take 4 hydrogen atoms and ram them together, you're left with an atom of helium. When we talk about the sun, the process is a little more complicated. When the star tries to carry out that fusion, positive protons repel each other. It takes a lot of force and energy to somehow squeeze them together. Fortunately, there's a magical force in space. It's gravity. The sun takes up 99.8% of all the mass of the solar system. Pretty heavy, right? And all this mass is what holds the sun together with the help of an incredible gravitational force. So, gravity takes quadrillions of these little hydrogen atoms and pushes them together every second of every day. And when they collide, they release some energy. So, unlike fire, the sun doesn't need oxygen to live. It needs hydrogen. And we all know that water is H2O. It consists of hydrogen and oxygen. So this is literally fuel for the sun. It's like trying to put out a fire with gasoline. More importantly, the extra mass added by water will make the sun heavier. Now, gravity says, "Thank you for your help." And then it starts to collide protons with each other even faster. And thanks to this, the synthesis speeds up. Great, we've made the sun incredibly strong, and now it has eaten us, along with other nearby planets. And if we keep adding water, the sun will sooner or later collapse in on itself. It will blow off its outer layers and become a black hole. Awesome! Now it will pull inside absolutely everything around. Good job, guys. Let's press rewind because clearly our water experiment was a mistake. One small solar flare sounds much better. Alright, we're back to our usual calm sun. But it seems like there's something that we've forgotten. Well, apparently water was critically important for life on Earth. Who would have thought? Now there's a huge amount of unmoving fish and other marine creatures lying around where the oceans used to be. Poor things. As for deep-sea creatures, they simply didn't withstand such a sharp change in pressure. Algae and corals have also dried up. Wait a minute, weren't they responsible for producing 50 to 80% of the world's oxygen? Oops, it's time to put on some oxygen masks. And how are things on dry land? I mean, now everything is just land. But you get the point. Wow, this whole place is lit, and I mean it literally. If there are no oceans, then there are no clouds or rain. Now there are forest fires everywhere. Poor animals have to escape and leave their homes. Oh my. And it's not like they'll be able to find a new home, because all plants, of course, will dry up quickly. There will be literally no place for living left on the planet. So now Earth looks like a giant desert. Great! But people have been living in deserts for thousands of years, right? Maybe they'll know what to do. They won't. After all, people in the desert also need to drink. So now there's total chaos everywhere, and survivors fight for the last drops of water. If there are any survivors at all. In fact, no matter how much they fight for resources, their fate is sealed. The ocean absorbs a huge amount of CO2 and the heat coming from the sun. They also distribute this heat throughout the planet, making it pleasant to live on. But once they're gone, the temperatures will quickly jump to 250 degrees Fahrenheit and above. But even if we forget about the high temperatures, now we have no clouds, and they helped us too, by not letting through solar radiation. So we're also under the direct impact of the sun's rays. Our last hope is icebergs. Now that everything is terribly hot, they've melted. And maybe they'll be the last hope for humanity. But that cool solar flare was definitely worth it. Silly humans.
What would happen if our planet turned into two separate ones, one consisting entirely of land and the other one of water? Could we survive on any of them, and how? Well, you're lucky, because I'm going to answer this question right now. So let's imagine that our Earth has turned into two separate planets sharing one orbit. Let's call these hypothetical planets rock and water. I know, very original. Anyway, let's start with the rock because this one is much easier to imagine. All we should do is ask, what would happen if all the oceans on the Earth suddenly dried up? Now, we know that water is life. It covers 70% of the surface of our planet. There's so much water that even if all the oceans and seas disappeared, some of it would still be left in underground rivers, streams, and so on. But unfortunately, it would not be enough for us to survive. All sea creatures disappear. After some time, all other animals, plants, and of course, people share their fate. Completely dried forests burst into flames sooner or later and burn until there is nothing left but ashes. But hey, it's not that bad. Well, it is bad, but life can still exist in some form. There are some bacteria that make cockroaches jealous. They're able to survive absolutely any conditions. For example, extremophiles have already evolved to live without water. These little guys can survive in an incredibly hot or acidic environment without water or even sunlight. Without them, the rock becomes an empty, lifeless planet. Although, who knows? Maybe someday extremophiles will be able to evolve into some wildly cool forms that can survive literally anywhere. But for now, the rock is just a floating rock, basically. Oh wait, did you imagine a hot desert or some sort of red-hot steppes? Surprise, surprise! This planet is actually extremely cold. You see, without water, there would be no atmosphere. The atmosphere consists of a concentration of various gases, including hydrogen and oxygen. Some H and O. You know where this is going, right? Yep, no water, no atmosphere. And since it is the atmosphere that accumulates all the heat we need, the planet would be very cold without it. The contrast between cold and less cold places also becomes very sharp. You see, water is basically a climate stabilizer. The oceans absorb almost all of the heat of our sun. They distribute it evenly over the Earth to make sure it doesn't get too cold or too hot. So without it, the rock gradually turns into a cold desert. The average temperature on this planet is around minus 100 degrees Fahrenheit. At both poles, the temperature is extremely low, about minus 300 degrees. And even in the warmest places, it doesn't exceed 20 degrees. These warm places are now the former oceans, because their dried-up depths are located much closer to the hot core of the planet. Wait, I hope you don't imagine this planet as covered in snow either. We don't have any water at all, remember? It's just a very cold rock. At this point, we're just a bigger and browner version of the moon. The moon is basically a waterless piece of Earth, after all. But hey, what happens to volcanoes? They're basically our last hope to stay warm, aren't they? Unfortunately, volcanic activity is decreasing due to a lack of water. You see, volcanoes and their eruptions happen because of the collisions of two tectonic plates, the oceanic and continental ones. The weight of the water presses on the oceanic plates. They go under the continental plates and form volcanoes. So, if there's no water weight, then there's no volcanoes and volcanic activity drops significantly. The rock now is just a planet full of many incredible high mountains, and every time the tectonic plates collide, they form more and more of these mountains and trenches, including some very big ones, like the famous Mariana Trench. I would say, be careful not to fall, but hey, there's no one to fall there. Also, there's no weather anymore. No water means no more snow, ice, or rain, or even clouds. The wind would probably be quite strong, though. Well, that's the fate of the planet rock. Not very bright, so let's just go see how the water planet is doing. Many, many billions of years ago, I wasn't around then, our Earth actually was a planet entirely covered with water. Then, about 1 billion years ago, the sea level dropped. The land appeared. This has changed the atmosphere of our planet forever, and that's how life was born here. But what happens if it returns to its original state? Well, to answer that question, we should first learn more about the ocean planets. So, what does one of these look like? Oh, sorry, I almost forgot. We have no idea. We haven't found any planets of this type because they're incredibly rare. I mean, there is one planet that is low-key and could be called an ocean planet. Yeah, I'm not even going to try and pronounce that. Still, even this one doesn't look the way you probably imagine. The water on it is in a very weird, unique state. Scientists have called this hot ice or superliquid water, and we've never seen anything like this before. In general, though, the actual ocean planets are very hard to find due to many physical reasons. These planets require very specific temperatures, pressures, and so on. But alright, just hypothetically, what would such a planet look like? Well, first of all, of course, it cannot be made entirely of water. I hope you didn't actually think that there could be just some gigantic water blob spinning around a star. It should still be a planet with a core and some kind of foundation. So let's just imagine that all the water on the former Earth has mixed into one giant salty ocean. Wow, that would be a dream come true for the sea creatures, but not for the rest of us. The only animals that could survive in this situation, except fish, are probably the birds that can swim and feed on fish. Now, I think even if the sea level rose significantly, at least a couple of islets could still stay above the water. Such islands would be the former peaks of huge mountains like Mount Everest. So, if these birds build their nests there, they can even survive for some time. But what about you and me? Well, we still have a chance. If we had enough time to prepare for the huge flood, we could stay safe either in giant submarines or on giant ships. We can grow food on board and fish from the ocean. But without the Everest Islands, we are unlikely to last long. If something breaks and we have nowhere to dock, we won't be able to fix it. Unfortunately, we no longer have drinking water. Now we can get it only from rain or by filtering seawater. But we have to store it someplace, right? And all these water containers would take up a lot of space and be very heavy. But in general, planet water is not as bad as it might seem. It's quite warm. The average temperature here is about 50 degrees Fahrenheit. And the gap between the lowest and highest temperatures is minimal, from minus 20 degrees at the poles to 70 degrees at the equator. Compared to planet rock, this ain't bad at all. Planet water would also be slightly larger than the Earth in radius due to the volume of, yes, water. The density of this planet would be, on the contrary, quite low. The gravity could become a bit weaker, too. Now, as for both planets, if we place them in the Earth's orbit, after some time, they would still move away from each other and follow different trajectories. They would have aligned themselves not to collide with each other. On one of them, the year would last 12 months, and on the other one, 10 or 11. And that's about it. A fun fact: all of this can actually happen in the future. First of all, the Earth's crust is gradually becoming thinner. Hey, I like thin crust. On my pizza. On my planet, not so much. So, one day, water can really flood our entire land. On the other hand, in a couple of billion years, when our sun begins to expand and turn into a red giant, all the oceans on our planet will really dry up. Alright, take a deep breath and shake it out. That's enough of this grim fairy tale. It's a waste of time to worry about such things so far off when, today, I can't find my wallet anywhere. I thought I put it over here.
When we look at our planet from space, one color dominates. That's why Earth is called the blue planet. About 3/4 of our world is covered with water. But there's a catch. 96.5% of this water is trapped in the oceans. And if you remember the first time your parents took you to the seaside, drinking that water is a big no-no. So, why is ocean water salty and undrinkable? There are two main reasons. The first is runoff water from the land. Rainwater is slightly acidic. Its pH factor is somewhere between 5 and 5.5. For comparison, pure water has a pH factor of 7, and the acid we find in batteries is a bit more than 0. Such rain erodes rocks when it falls on the ground. This releases ions, such as sodium and chloride. They end up in rivers and streams that eventually empty into the ocean. Living organisms remove some of the good ions, but the rest remains. Over time, this increases their concentration in the water. Oceans have their own salt powerhouse. Vents in the sea floor let out a hydrothermal fluid. Sounds complicated, but it's easy to understand. Water seeps down the gaps on the ocean floor. Then, the magma from the Earth's core heats up the water. There is a chemical reaction that frees seawater from oxygen. It picks up metals, such as iron and zinc. The vents on the sea floor release this metallic water back into the ocean. During an underwater volcanic eruption, the process speeds up. Salt and other minerals are directly released into Earth's oceans. Over time, salt accumulates on the seafloor and forms domes. These deposits occur under dry land as well. Some places on the globe have a large number of salt domes. The Gulf of Mexico is just one example. Beneath the waves, they affect the salinity of water. Other factors that determine how salty a body of water is include evaporation, air temperature, and precipitation. The general rule is that salinity is low near the equator and at the poles. All the oceans and seas in between are likely to have high salinity. Scientists estimate that dissolved salts make up 3.5% of the weight of the world's seawater. The waters that empty into the ocean, such as lakes and rivers, are fresh water. So, why is the seawater salty? To answer this question, we must travel into our planet's past. Researchers believe that primeval seas weren't as salty as they are today. But over time, rainfall washed away the rocks on land, transporting vast amounts of salt into the oceans. The process has been going on for more than 3.8 billion years. Today, some 4 billion tons of dissolved salts end up in Earth's oceans every year. The input and output of salt are fairly balanced. This means that seawater's salinity is stable. So, why can't we drink seawater? We already take salt into our bodies with food and drinks. It is called dietary salt. The World Health Organization recommends that humans consume no more than a teaspoon per person, per day. You shouldn't go over that amount if you want to keep your heart healthy. Centuries ago, salted beef and pork were the standard diet of seafarers. Meat was preserved using salt. At sea, fresh fruit and vegetables would go bad after just a couple of weeks. Before refrigeration, this was the only way to keep food fresh. Pickling was another option for storing food. The reason why we can't drink seawater is the salt content. The percentage of this mineral in our blood is nearly 4 times lower than the percentage of salt in seawater. Our body simply cannot process such a high amount of the substance. When we intake salt as part of our diet, we also drink liquids. When you serve pretzels, you probably have a glass of water or juice nearby. It helps quench the thirst and keep the salt levels in check. If we drink water straight from the ocean, the exact opposite happens. We just become thirstier. Our body absorbs both water and salt. They end up in our bloodstream. The organs responsible for getting all this salt out of our blood are the kidneys. But they need water to perform their duty. The higher the salt content, the more water they need to wash it away. When the process repeats itself several times over, you become dehydrated. This is the process of losing water from the body. And there's another catch. You start releasing more water than you take in when you drink seawater. The difference leaves you thirstier than you were when you started drinking seawater. Not a good idea to begin with. But some marine mammals, such as whales, seals, and even seagulls can drink water from the sea, just like we drink tap water. The kidneys of these mammals are super efficient. Birds have special glands in their beaks that prevent salt from getting inside their bloodstream. Scientists found that the only land animal that can drink seawater is the camel. And if you ever wondered if fish drank seawater, they do. The gills and kidneys help them pump out the excess salt. For humans to drink ocean water, it first needs to go through desalinization. This is the process of removing salt from seawater, and there's a lot of it to take away. Estimates show that if we laid out all the sea salt across Earth's landmass, it would be higher than the Statue of Liberty. That's why desalinization on a global scale isn't realistic. Right now, less than 0.5% of the drinking water we produce comes from seawater. And the demand for potable water is only going to increase. The current rate of consumption means that the demand for fresh water doubles every 20 years. The biggest issue with desalinization is the energy cost. It takes 10 times more energy than other water production methods, and the carbon footprint is huge. Large desalinization plants often need to have their own power stations. This is all because of the technology behind the process. Salt dissolves easily in water. It creates a strong chemical bond with water that is hard to break. Desalinization facilities mostly use reverse osmosis to achieve this. Large pumps exert pressure on seawater to push it through a filter. Its membrane is so fine that each pore is a fraction of the size of a human hair. The filter allows for water molecules to pass. Larger salt molecules remain trapped in the membrane. For every quarter of a gallon of fresh water the plant generates through desalinization, there is the same amount of water that is now twice as salty. Hardly the ideal method of water purification. The idea that humans could drink seawater isn't new. In the mid-4th century BCE, the famous Greek philosopher Aristotle considered using a series of filters to remove salt from water. Ships in the 16th century had small, portable distilleries that could boil seawater. This was merely patchwork, since exposing seawater to high temperatures doesn't make it drinkable. Such thermal processing only sterilizes the water. You would need to catch the steam that evaporates and wait for it to cool down before it's safe to drink. This is a complex and time-consuming method that is probably not worth the effort. Let us imagine for a second that we got rid of all the salt from the Earth's oceans. We would get an endless supply of drinking water. But at what cost? There are millions of animal and plant species that are adapted to salt water. These include plankton, the basis of all marine life. They wouldn't have enough time to adapt to the new conditions. Not all fish are like the salmon, which thrives both in fresh and salt water. The sudden switch would also have a profound effect on our planet. Since freshwater is less dense, it would immediately cause the ice cap in the Arctic to sink by 4 inches. This would trigger the largest tidal wave the planet has ever seen. Although the idea of desalinization on a global scale sounds good on paper, we should take it with a grain of salt.